Welcome to this lecture series in linear algebra. In this lecture, we look at the notion of complexification, by which we construct a complex vector space out of a real vector space, and we'll see nice applications of it. In particular, we'll be proving that any endomorphism on an odd dimensional real vector space has an eigenvalue. All right, so let us recall the relevant things. So first of all, we need to know what are eigenvalues and eigenvectors. So you should maybe brush up on it if it's not immediately obvious or clear or it's not on your fingertips. We need to know the fact that every complex endomorphism has an eigenvalue. By this we mean an endomorphism on a complex vector space. We proved this. And let us also recall this age-old fact that if we have an endomorphism on a vector space and U is a T-invariant subspace, which is to say that T of U is contained in U, then this diagram commutes where this is the natural projection. This just takes V to the corresponding coset. And of course, T is the map T, and this map takes a vector to this. So this diagram commutes, and T bar is a linear map. So once you have a T-invariant subspace, then there is an endomorphism that is induced under quotient by the endomorphism on the parent vector space. All right. Here are some problems for practice. Now let us get started. So we start with a real vector space, and as usual, it is finite dimensional. We consider the set V cross V as, well, V cross V is just the set theoretic cross product, but let me write it. So it is all those ordered pairs where both the coordinates come from V. That's what V cross V is. And we will define a complex vector space structure on V cross V. There is a real vector space structure on V cross V, just the direct sum construction. But we will define a complex vector space structure on it as follows. So let me call this W so that it's easy to write. So to define a complex vector space structure on W, first we need an addition map. So the addition will be defined coordinate wise. So the definition is U1 comma V1 plus U2 comma V2 is defined as U1 plus U2 comma V1 plus V2. Okay, and we need a multiplication map from C cross W to W. And this is interesting. So this is not a simple map. So let me write down the definition and then explain where it is coming from. So we define alpha plus I beta dot U comma V as alpha U minus beta V comma beta U plus alpha V. So it's not clear what's going on. Why would anyone come up with it? But here is the motivation. So we are thinking of U comma V as U plus IV formally. So alpha plus I beta times U plus IV, if you just formally apply, how you multiply complex numbers, this will turn out to be this times that, then this times that, but I times I is minus 1. So kind of the real, quote unquote, the real part would be alpha U minus beta V, and quote unquote the complex part would be alpha V plus beta U. So that is what's going on in the definition. This is what motivates the definition, right? So once we define these operations, here is the exercise. Check that. And W with these two operations, plus and dot, is indeed a complex vector space. That's a simple exercise. Another exercise is show that the dimension of W, where of course we are thinking of W as a complex vector space, so I'll qualify that with a subscript. This is same as the dimension of V, where of course V is a real vector space, so just to emphasize that, I will write a subscript there. So the complex dimension of the complexified thing, does not change. The parent space was a real vector space. It had some dimension, but it so happens that this guy as a complex vector space has the same dimension. It may seem a bit surprising, but it is not if you think about it. Yeah, so this is called the complexification. Let me first say that this is called the complexification. So W is called the complexification of V. And to give a hint as to how you prove this, this is, just one way to prove it is the following. Let V1 up to Vn be a basis of V. Then one can show that this thing is a basis of W. It may seem wrong, but it is actually true. And of course, to prove it, first you just assume that the dimension of V is 1 and then verify this, and then dimension of V is 2 and then verify this, and then you can immediately see the pattern. Anyway, so that's there. And now we need one more thing. So just like we have a vector space we have a vector space V which is real, and we extract or construct a complex vector space out of it. Suppose we were given an endomorphism. So let T be an endomorphism on V. Then we can also get an endomorphism on W. So define T tilde, for the lack of a better notation, from W to W as T tilde U comma V equals TU comma TV. So this is a map, and you can check that this is a linear map. So that is another exercise. Check that T tilde is linear. When I say linear, I mean complex linear. And this T tilde will be called the complexification of T. So not just that you can complexify a vector space, you can also complexify endomorphisms, right? So that's just some definition, some construction. It's not clear why is it useful, but now we will see why is it useful. So suppose we have a real vector space and we have an endomorphism on the vector space. Then there is a T invariant subspace U of V whose dimension is either 1 or 2. So what did we know in the context of a complex vector space? If this were a complex vector space, we knew that any endomorphism has an eigenvalue, and therefore it is same as saying that there is a one-dimensional T invariant subspace. But in the case of real vector spaces, we cannot say something as strong, but not quite as weak either. We are pretty close. So it says that there is a invariant subspace whose dimension is, if it is not 1, then it is 2. So it's a little bit of a payoff. All right. So let's prove it. So let W be the complexification. Let W be the complexification of V as discussed in the previous slide, and T tilde be the complexification of T. Complexification of T. All right. So since T is a complex endomorphism, we know that there is an eigenvalue. So let lambda plus I mu is be an eigenvalue of T tilde. So we can find, so let this be a non-zero vector in W, be non-zero, and the 0 of W is just 0, 0, where this 0 is the 0 of V and this is the 0 of W. So one can easily check that this indeed is the additive identity of W, be such that T tilde applied on this vector is equal to lambda I mu applied on multiplied with the same vector. So this implies what? This implies, by definition of T tilde, this is Tu comma Tv. This is equal to lambda u minus mu v comma mu u plus lambda v, which implies tu is equal to lambda u minus mu v, and tv is equal to mu u plus lambda v. So these two things imply, these two equations imply in particular that tu comma tv are in span of u comma v, which means what? Which means span of u comma v is t invariant. And now since u comma v is non-zero, at least u or v is non-zero, meaning both of these cannot be 0. So the dimension of this space is at least 1 and at most 2. And therefore we have a, if you just declare that as capital U, this space as capital U, we have a dimension 1 or 2 subspace, which is t invariant. So the last line I don't want to write. I can write the last line. So that's a very nice proof. And this has a nice consequence. So again, we have a real this time we have an odd dimensional real vector space, and we have an endomorphism on the vector space. Then we claim that this endomorphism has an eigenvalue. So we will see that odd is important. Without this odd dimension hypothesis, you cannot claim that this is the case. So first let's prove it, and then we'll see an example for the even case. So here is the proof. So assume on the contrary that the theorem is false. Right? So if the theorem is false, there is some counterexample, meaning there is some vector space of odd dimension, some real vector space of odd dimension, and an endomorphism which does not have an eigenvalue. So we will start with, so let V be an odd dimensional real vector space of smallest possible dimension. Smallest possible dimension such that there is an endomorphism on V without an eigenvalue. So once again, first we assume that the theorem is false. Then there exists a counterexample. So there are odd dimensional vector spaces and endomorphisms on them such that this endomorphism does not have an eigenvalue. So amongst all those vector spaces, we can pick one with smallest possible dimension. There could be multiple such spaces and multiple such endomorphisms, but we just pick one example. Just pick one counterexample to the theorem, but with the property that the dimension of the vector space is smallest possible. That we can do. Formally, we are using the well-ordering principle. Okay, so by the previous result, we have a subspace of V, such that it has two properties. U is t invariant, and second property is that dimension U is equal to 1 or 2. But since t does not have an eigenvalue, and since U is t invariant, the dimension of U cannot be 1. Because if we had a one-dimensional t invariant subspace, we would have an eigenvalue. So it is forced that the dimension of U is 2. Right? So we have a two-dimensional t invariant subspace. And now we have this diagram, which we recalled in the beginning. Right? We have this. So T bar is an endomorphism on V mod U. And what is the dimension of V mod U? Dimension of V mod U is dimension V minus 2, because dimension of U is 2, which is odd. Right? So V mod U is an odd dimensional vector space whose dimension is strictly smaller than the dimension of V. So that's the important point. The dimension of V is strictly greater than the dimension of V mod U. And since T bar is an endomorphism on it, by the minimality of the dimension of V, T bar has an eigenvalue, because this is an odd dimensional real vector space of dimension smaller than the dimension of V. So this has an eigenvalue. So let v plus u in v mod u be non-zero such that t bar of v plus u is equal to lambda times v plus u for some lambda. For some lambda in the base field, which is reals. Right, all we are using is the fact that this has an eigenvalue, call it lambda, so there is a non-zero vector in the vector space such that this equation is satisfied. So if you just use the definition of t bar, this gives that tv plus u equals lambda v plus u. That's how quotient spaces behave. So this means that tv minus lambda v is in u, which implies that t minus lambda I applied on v is in u. Okay. At the same time, since this is non-zero, v plus u is a non-zero vector in v mod u, we also know that v is not in u. This is exactly the same as saying that this guy is non-zero. Right? So let's keep this data with us and continue. So we claim t minus lambda I has a, so let's call t minus lambda I as s. So let s equals t minus lambda I, and the claim is that S has a non-trivial kernel. Once we prove that S has a non-trivial kernel, we'll be done, because then this would have a non-trivial kernel and hence lambda would be an eigenvalue of t. Okay, but this is very simple because the reason is very simple. Oops. So note that this subspace span of V plus U is a subspace of V, which under S maps inside U. Why is that? Because what is the image of V under S? SV is in U. This is what we saw here. This is SV, the left hand side, and this is U. So S of V is in U, and S of U is also inside U because U is T invariant, and hence it is also invariant under this. So just understand this containment. We have this containment, but this is a three-dimensional thing because little v is not in U. So the dimension of this guy is 3, and the dimension of this guy is 2. So if you just think of S as, just restrict S to this particular subspace. S is an endomorphism of this particular subspace by restriction. We see that it is mapping a three-dimensional thing into a two-dimensional thing. And you can use rank nullity to establish that the kernel of S must be non-trivial. So that's it. That's the proof. ... You can write that down. The kernel of S is non-trivial, and hence lambda is an eigenvalue of T. That's it. And for an example where you have an even dimensional space and an endomorphism without an eigenvalue, I think we saw this. So the example that we saw was T from R2 to R2, which was given by Te1 is E2, but Te2 is minus E1, and this does not have an eigenvalue. So we saw this, and so that's the end of this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.